So in order to apply L'Hopital's rule, we have to get 0 over 0 or some kind of infinity over infinity. So if we get something like 0 times infinity, it would not work. But oftentimes when we get a different indeterminate form, we can first rewrite it and then take the limit and get it into the 0 over 0 or infinity over infinity form. So let's look at what we mean here by an example. So let's look at the limit. I mentioned that this does work for one-sided limits. So let's look at the right-hand limit as x approaches 0 of x ln of x. Okay. If we just plug this in directly, the limit as x approaches 0 from the right of x is 0. The limit as x approaches 0 from the right of ln of x is going to be positive infinity. Okay. So you should just be able to see that just from the graph where it looks like this, right? If you're approaching 0 from the right, it's going to be negative infinity, not positive infinity. But same idea, right? It'll be negative infinity. So you get 0 times negative infinity. This is an indeterminate form, but it's not one of the indeterminate forms where we can apply L'Hopital's rule. It's not even a ratio anyway, right? So we need some kind of ratio, and we need this 0 over 0 or infinity over infinity form. So what we could do is we can rewrite the function. This one in particular, we could rewrite it as ln of x over 1 over x. Okay, so these would be equivalent. You could take ln of x and times it by the reciprocal of x over, or 1 over x, which is x over 1, and then you get x ln of x. So this is a common trick in order to get functions in the right form to apply L'Hopital's rule. Now when we apply this, we get negative infinity over positive infinity, actually. Right, but it doesn't really matter. It's just that we get some kind of infinity over infinity. So now we can apply L'Hopital's rule. The top is going to be 1 over x. The bottom is negative 1 over x squared. So maybe a good idea to simplify this a little bit first. Oops, sorry, didn't notice it was cut off there. So 1 over x times negative x squared over 1. So negative x squared over x is going to be negative x. And this is just going to be 0. Okay. I dropped the right-hand limit, but it actually wouldn't matter here. Okay. So we were able to rewrite this, even though we couldn't apply L'Hopital's rule in the beginning. We could rewrite it and then apply L'Hopital's rule to get that this limit is equal to 0. All right, let's try another tricky one like this. So let's do the limit as x goes to infinity of x to the 1 over x. Okay, so if you just plug it in directly here, you're going to get infinity to the 0. So again, this is an indeterminate form, but not one where L'Hopital's rule would apply. And again, we don't even have a ratio to apply it to anyway. So there's a few different ways you can do this one. The way I would prefer to do it is to use the e to the ln trick. Okay, where you write it as e to the ln of this, because then that allows you to bring the derivative down. And actually, let's just look at just this part of it first, so I don't have to write the limit over and over again, just until we get it into a proper form. So this is e to the 1 over x ln of x. Okay. So then this is, we could think of e to the ln of x over x, right? So now when we go to do that limit, we're doing the limit of e to the ln of x over x, right? Remember, by limit properties, this is equal to the limit e to the limit of ln of x over x. So even though it's in the exponent, we're still just looking at this limit. So this is equal to still the limit as x goes to infinity of the derivatives 1 over x over 1. Even though it's all in the exponent, it still is equal. And sorry, I should have showed that this is equal to infinity over infinity at this point. But it is, right? ln of x goes to infinity, x goes to infinity. So now the limit as x goes to infinity of just 1 over x now is 0. So this is e to the 0, which is equal to 1. Okay. Okay, so I'll do one more here. So this is kind of a special one where you can show, so we want to show that the limit as x goes to infinity of 1 plus 1 over x to the x is equal to e. Okay. This actually comes up in compound interest, interestingly enough, where like the formula for compound interest, the general formula is p's the principal, sorry, this should be the future value. The future value at time t equals the principal times 1 plus r over n times to the nt, where n is the number of times you compound the interest every year. So how many times the interest is applied every year. So if you take the limit as n goes to infinity, you have continuously compounded interest, and you come out with this formula p times e to the rt. Okay, so it's a little bit different from ours because we're only looking at 1, but you could change this to like 2 or something and do something similar and show what the limit ends up being. This is an important formula, so let's show that this equality here is true. So, right off the bat, if we just plug it in, we will get, really it's hard to even say what exactly we get, right? Because we can't really bring the limit inside because we have this x outside. So I think it's better just accept that, it's just a weird quantity in general. It's some kind of indeterminate form. And just go ahead and try to rewrite it. So again, I'll rewrite it without the limit first, and then we'll bring the limit back later. So we're going to do the same thing. We're going to do e to the ln of this thing. I'm going to use the exp notation so that I don't have this whole big thing in the exponent here. Okay. So this just means e to the ln of all of this. It's just a different notation for it, exp of the thing. So now we can bring that exponent down. X ln of 1 plus 1 over x. And then just like before, we want to rewrite this as this over 1 over x. Okay. So now we can take the limit of this. So we'll do the limit as x goes to infinity of the exponent of ln of 1 plus 1 over x over 1 over x. And again, with the limit laws, we can bring the limit inside here. So let me just rewrite it so I don't have to rewrite the entire thing. This is going to be equal to the exponent of the limit. Okay. So the limit as x goes to infinity of the top, we take the limit as x goes to infinity of 1 over x, so that's 0. So we get natural log of 1. So this is 0 on the top, and then on the bottom, that's also going to be 0. So we can apply Lhopitals rule in the top there, or in the exponent. So we get the limit as x goes to infinity of the derivative of this. So this is going to be 1 over 1 plus 1 over x. And then via the chain rule, we have the derivative of the inside, which is the derivative of 1 over x, because the derivative of 1 is 0. So negative 1 over x squared over the derivative of that, which is negative 1 over x squared. So these cancel, making this a little nicer. So we get the limit as x goes to infinity of 1 over 1 plus 1 over x. Again, the limit as x goes to infinity of 1 over x is 0. So this is just going to, this whole thing is going to end up being just 1. So this is e to the 1, which is just e. Okay. So using Lhopitals rule, then we show that the limit as x goes to infinity of this quantity is indeed e. And that's where that comes from in the compound interest formula. So you could try it out. You could use, like you could put r here, or you could just work on this formula, and you could try to modify this a little bit to show that this formula is true.